Dr. Carroll, and this video is about parallel programming. I've got a couple objectives for you to learn as you go through this, and so by the end of it, I'm hoping that you can appreciate that modern computers have multiple processing units, and we'll see some pictures of that, that you can be able to describe the role of a concurrency platform, that you can do the calculations for speed up and efficiency, and be able to identify a race condition in code and why it's a race condition, and describe how and why an algorithm is parallelized. So with some examples at the end with matrix multiply and merge sort. So that's a lot. Let's jump into it. So let's start off with talking about parallel systems. We have access to several parallel systems. Your computer probably has multiple cores on it. Your phone could have, your watch even could have multiple cores on it. You could have a GPU with multiple processors on it. And this scales up to clusters and cloud computing. So which ones have you used before? And how many cores does your computer have? How many does your phone have? Those are some interesting questions to answer to just understand how ubiquitous parallel programming is. Here's a picture of a chip from AMD. This is blown up a lot. What I want you to do is look at this and look at some symmetry here. Now we can see that there is some regions that are repeated here. And so this chip is going to have multiple cores on it built into it. Here's a different chip with the different parts specified. This is an 8-core chip, and they're labeled here, and it has the memory spread out and the core units spread out. And so we can see chips, and these are several years old even. Chips have multiple processing units on them. And when we go to program them, there are two main memory models. We have the shared memory model and the distributed memory model. With the shared memory model, all cores have access to the same memory. That's a lot like what we've been seeing. Distributed, they all have their private memory and they send messages to other cores. And so we're going to be focused on shared memory today, but both memory models exist in practice. There's two main features of the shared memory model. It has multiple threads, and it has this concurrency platform that handles the scheduling and load balancing and things like that. One of the constant trade-offs with parallel programming is load balancing versus communication. There's two main approaches to this. Data partition, how are we going to divide up the data to be shared, and task partitioning, who's going to do what. You can see that there's some overlap there, some different ways to look at it, but these are two different ways to divide up all the work. When we're talking about parallel programming, there's some vocabulary we need to establish. When I say the word node, that means it's a box that has processors, memory, disks, and a network connection. Okay, so if you think about if you're looking at a rack and you're plugging it in, that's a node. A cluster then is a whole bunch of nodes put together, and a node could easily have more than one CPU on it. So now that we have multiple machines, we want to say, hey, what's the performance of this? So we have a very common metric called speed up. Speed up is very simple. Take the time it takes to execute with just one processor, T sub 1, and divide it by the time it takes to execute it on all the processors, and that's your speed up. It's also interesting to be able to track efficiency, which is speed up divided by P, the number of processors. We'll see some examples of those, of code running and speed up and efficiency, to understand them better. So with speed up, adding more processors does not always improve the speed a code runs. Usually we can get better speed up, but up to a point. There's a part of the code that isn't parallelizable, and so it's going to scale linearly with the problem size. And the parallel part, though, we can only get so much gain out of that. Generally, we can handle the efficiency, or the performance does best for big problems, and it degrades as the problems are smaller. Then our performance is going to degrade. Another important concept is scalability. Remember how I talked about the non-parallelizable part of the code and the parallelizable part of the code? Well, those are two different portions, and they could be staggered, but we talk about them as a whole. And so Amdahl's law helps us to understand what we could expect if we have an alpha, where alpha is the portion of the code that cannot be parallelized, and we have a number of processors. And so let's see Amdahl's law played out. Here I produce this graph. Look, the X scale has the number of processors. Notice it's logarithmic. The Y scale is also logarithmic. It's the speed up. There's a predominant line there, the red line with the pluses on it. That's linear. That's perfect. That's what we'd hope for. If we had 10,000 processors, we'd hope for a speed up of equal amount. Well, what do we see? If alpha is 0.01, 1% of the code can't be parallelized, then that's not very much, right? But notice what happens when we have 1, 10, and going up in number of processors. We diverge from the ideal of linear. Even at 100, there's starting to be a noticeable gap. And also notice that it is leveling out as well. Well, this becomes more pronounced the higher percentage of non-parallelizable code that we introduce. So a 5% of the execution not being parallelizable, we notice that it diverges more quickly from ideal, and it levels off sooner. And as it goes higher and higher until we have a ridiculous amount of 90% of it can't be parallelizable, then why are we running it on multiple processors anyway? So this is to visualize Amdahl's law and the different percentages and what they actually mean in terms of number of processors. Let's talk about communication. So communication is super slow. You can do thousands or millions of computations in the time it takes to pass a message. So you could significantly speed things up if you can do some more calculations, by more, like thousands even is okay, to figure out how to communicate less. And so there's a simple equation that helps us understand about how long it's going to take to send a message. If S is the size and B is the bandwidth and L is the latency, then we take the size of the message divided by our bandwidth, how fast we can set it out, but we always have this latency. No matter how big the message is and how good our bandwidth is, we always have that latency. And so that's how long it takes us to send a message. I've worked in a number of different environments for high performance computing, and so people spend a lot of money on low latency, high bandwidth systems so that they can send messages very quickly. I want to talk about OpenMP to help us to solidify some of these concepts and to put them into practice. OpenMP is a concurrency platform that I talked about early on. It's going to be a way to manage and schedule and help us to take Fortran and C and C++ code and quickly allow them to be parallelized. It uses threads to achieve parallel programming. It's going to use a fork and joins model. Hopefully you're already familiar with those two concepts. Excuse me. And so it gets speed up by having the operating system split up the threads among multiple CPUs that already exist on the machine and leveraging them instead of just a single CPU. New threads are explicitly created, and we'll go into that. Let's start by just making sure we have a foundation on forks and joins. On the top here, we show an execution. We have one thread, and it goes through and it has a task that could be parallelized, but we're not doing it because we're only doing it on one thread. And so it does part A, part B, part C, and then we're done with that. It has to do some collecting part. Then we move into another set of the execution, and this could be parallelized. And notice not all the pieces are the same here. A is larger than B and about the same size as C, and D is about the same size as B. Once we're done with that, we need to collect things, and then we're to a third part that could be parallelized, but we're doing it on one thread. So we do all of part A, and then we do all of part B, and then move on. If we were doing this with forking the program and then joining it back together, we'd have the bottom half of the diagram. And so the master thread is shown here skimming the top. And so we'd come along and then we would fork off two other processes to handle the parallel task 1B, part B, and part C, while the master thread executes part A. And then when that's done, it would join back together, and then the master thread would fork off three new threads to execute parallel task 2, B, C, and D, while it does A. Notice if we're forking them off and we're waiting for everyone to be done, it's going to take the same amount. We have to wait the longest amount of time of any of those parts, which is why we want to make sure they're balanced. And then for the last set, the parallel task 3, it's just going to fork one off, and then master thread will execute A while another thread B. And so that's the fork and join model that is going to be utilized by OpenMP. OpenMP from Lawrence Livermore National Labs has a couple goals. It wanted standardization. It wanted to be very simple, only 3 or 4 directives, easy to use, and be able to be applied to Fortran, different versions of Fortran, C, and C++. Note, you can't use OpenMP and Java together along with other languages. Maybe you could work on making that a possibility. So the programming model that OpenMP uses is a shared memory model, thread-based, explicit parallelism, we'll talk about that in a second, using this fork join model that we just talked about, compiler directives, which we'll talk about, and then most implementations are nested parallelism support. It's going to dynamically create the threads, and it's not using I/O to send messages. Let's go through these. Explicit parallelism means you need to indicate in your code what sections that you want to be parallelized. And so they're going to vary between languages. I'll give some examples in Fortran because I thought that'd be interesting to do. And so these directives are ignored when the OpenMP flags are not set, which makes it real easy just to run in a serial version with one thread, one CPU. And then otherwise we could say, no, I want it to be compiled now with taking parallelism into account, and then it's the same code base. It also interacts with environmental variables to execute different number of threads. And there are library routines to allow the programmer to set and access system variables. Notably, it is not a message passing paradigm like MPI, message passing interface. Instead, we're compiler directives to say, I want this part of it to be compiled to be handled in loops. So let's look at this. The top part here has Fortran. We're going to put that in a comment, and we're going to do bang $OMP and then our directives. And then we're also going to say, oh, this is where it ends. So it makes it really clear where it starts and where it ends. If you're doing C or C++, you'll use a hashtag pragma OMP and then the directives clause, and then you'll put that in curly braces so that it's in a structured block. I'm going to go through examples here in Java, in Fortran. Let's go through an example in Fortran. If you're not familiar with Fortran, it's very applicable in the computational sciences world. So let's look at a hello world program. In the top there, just 3 lines. We have some keywords and we can display hello world. So we need to compile it. We need to execute it. After it's been compiled, it defaults to writing executable to a.out. We execute that and we'll see hello world execute. Now, if we wanted to add in some OpenMP additions, we would put in these comments shown in gray here on my screen to tell it to be parallel, and then we're ending the parallel. And then we would hope that that would produce a parallel version. But what happened? What went wrong? Well, what we have to do is we have to give it a flag to the compiler to tell it, hey, I want you to not ignore those comments, those compiler directives, and use them. And then if we execute, we'll get multiple threads all executing the same thing. Here, they're all just printing hello world. Very simple. Here, I'm showing an example of setting an environment variable, OpenMP num threads, assign it to 3. Notice I didn't recompile it, but running it again, we're going to get just 3 threads running. And so we could dynamically change it without having to recompile it. Let's look at some more information about this, specifically thread ID. So here's a little bit more of a Fortran program. We are declaring that we want an integer, and that these methods here to get our thread number that's going to return an integer, and to get the max number of threads. And notice the keyword private here in the directive, that we're saying each of the threads gets their own thread ID and number of threads to have their own copy. And so if we execute this, then this is the thread ID and the total number of threads. What's going on here? The view in the parallel code is that it's kind of like an isolated sandbox. And so if you ask it, how many threads are there? It's like, oh, there's only one. It thinks that it's like its own little world. And so we need to pull the number of threads outside of the parallel loop to be able to get that. And then if we execute it again, it says, oh, yep, there's 8 threads. And the thread IDs range from 0 to 7. Also notice, it's not that thread 0 is reporting first and then 1, then 2. We don't know which thread will execute in which order. And if we run it again, they're going to be in different orders. This is because the CPU is scheduling, and that's very hard to know what the order is being. it would be erroneous to assume the threads are going to execute in order. Imagine you have 8 programs all doing the same thing and you said go. You don't know which one is exactly going to be the first one. So if we want to, it's common to parallelize a loop, and so we can do that with a directive to the do and then the end do on some loop. In fact, that's very common. We have a loop and we want to break it up and do it in parallel. So here's some code that just burns some carbon credits. It doesn't really do anything, but it's complex enough that it will compile and run, and it won't be optimized away because we're displaying the first value out of this array A here. And so we have a doubly nested for loop that the outer loop is going to run 100,000 times. The inner loop is going to run 10,000 times. We're doing some double precision real computation that's going to take some time to calculate that. A log, that's not very quick. And then we're going to do this, and we're telling it to do it in parallel. And if we execute this, we can see, yep, the seconds here is our y-axis. The x-axis is the number of threads, which, as I mentioned, we can control. We could do 1 thread, 2 thread, 3, 4, 5, 6, 7, 8. And notice it takes less time as we increase the number of threads in this trivial example. What's also interesting to note was that's the real time, like if you started a stopwatch. The user time, though, is the sum of all of the processes that are running. Notice what happens. The user time, the sum of all of them, actually increases. And so let's look at this a different way. Let's look at it in terms of speed up. So we have our starting point here, and I've shown the ideal as a thin gray line. Hopefully that shows up. If you're on your phone, you might need to zoom in on that. And so the speed up with 2, 3, 4 threads, we're getting close to ideal, but then after that, we don't get any more gains. We're not seeing more benefit there. It can't do any better. Well, what does this mean in terms of efficiency? Here, with 1 thread, we're at 100% efficiency. That's what we'd expect. And then with 2 threads, we're fairly close. 3 is just a little bit less efficient, 4 a little bit less, but then it starts to really drop off quickly with more because it's taking the same amount of time, but we've got more threads that are working, more cores that are executing. Imagine if you're paying someone to do a job. This is paying 1 person to do it, 2 people to do it. There's a little bit of overhead you're losing here. You're doing the same job, 3, but then you start paying 5, 6, and 7, 8 people, and the job's taking just as long, but you're paying more people. It's less efficient. With Fortran, we can combine directives all into one line to make it easier to just have the directive be one line. For example, if we have parallel, do, private, we can just put all of that on one line. Let's talk about a great example here. If we wanted to do numerical integration here on 4 divided by the sum of 1 plus x squared from -1/2 to 1/2, we could do that. And in fact, did you know that that's a definition of pi? And we can use Simpson's algorithm to do this numerical integration. If you'll remember from calculus, we're going to figure out how many partitions we want to break that up into, or what is that time slice. Then we're going to divide that domain, the x-axis, into that many partitions. We're going to evaluate the function at each of those partitions. then we're going to calculate the area because we're integrating, so it's the area under the curve. We're going to calculate the area of that small width times whatever the value is, and do a whole bunch of those, add those all up, and output the result. Well, guess what? This is very analogous to what we would do for parallelization. This is an embarrassingly parallelizable problem is the term. And so what we have a processing unit, it's processing element 0, and so we'll consider that as the driver for all this, and to get the number of partitions. How many partitions we're going to do, and we'll do it on just one thread. Then we're also going to determine, well, what's our total number of processing elements here, and we'll call that M. Well, we know how many partitions we want to calculate and how many workers, helpers, threads we have, so then we can divide up the domain, the x-axis, into n divided by m partitions. And then we can evaluate the function at each of those partitions, multiplying that times the width of that small area, add them all up, and then for the driver one, the processing element 0, then output the result, because we don't need to output 16 or 100 times, we just need it output one time. Well, here is some Fortran code to accomplish that. I've called it reduce. We have 10,000 steps we're going to do. We have our sum initialized to 0 before we get started here. We have our step size is going to be divided by the number of steps. And so we do a loop through all of those steps. And what we are doing is we're figuring out what our x value is and multiplying that by our step size here, and then evaluating 4 divided by 1 plus x squared, and then adding that to our sum and doing this a whole bunch of times, and then multiplying the sum by the step size, and then we get our estimate of pi. So we can see if we do it with 10,000 steps, we get 3.14139. Okay, we start to break down here from what pi is, but that's a decent approximation of pi. So, but let's do it in parallel. This seems like an embarrassingly parallelizable. Let me compile this for you. Let me put on my flag. It's wrapping around. There we go. And now let's execute it. And we get pi is about 1.75. Well, oh no. And it's changing. This is a terrible estimate of pi. What happened? Notice if we recompiled it without the flag and then executed it, we get our estimate as we'd expect. So what's going on here? What happened? What went so wrong? Well, let's talk about it. This is a good point to talk about race conditions. Let's do a simpler loop. Here we have 4 lines of code. X equals 0, we're going to do a parallel loop with I is 1 all the way up to 2, including 2. And in that parallel loop, we're going to increment x by 1. And then after we're done with the parallel loop, we're going to print x. Let's talk about a possible execution out of many possible executions that we could have for this simple code. We could have line 1 is done just on one thread, and so then we'd initialize x to 0. And let's say in this parallel loop that one of the threads starts and it takes x, saves it in a register, and then increments that register, but then the other thread is executing instead of it completing, copying that register into X. And so before it does that, the other thread, because we're doing it in parallel, copies the value from X into register 2. And hopefully you're seeing this problem here, that we have the value of X, it's 0. We're on step 4 now. The value in register 1 is 1, and now the value in register 2 is 0. We go ahead and increment the value of register 2 at cycle 5 here. Then cycle 6, we copy the value from register 2 to X, and that's 1. Then, so this thread is completed, it's part of the loop. So then we come back and we finish up the other one, and it copies the value from R1 into X. Now X, we ignored what was already there, and then we print it out. So X plus 1 plus X plus 1 equals 1 is what we have happen here. And so what we have is we have a race condition, that we have a situation where if a certain sequence of events occurs, then we have a problem. And the problem is here that this is not atomic. It takes 3 steps, and if we interrupt it and use X or assign X in that process, then we have the problem. And so that's what happens here. And so that is a race condition. Here's some more race condition, or some more code, a little bit more complex here from the introduction to algorithms. We have a matrix vector code here that is wrong. It's in the method name. So we get how many rows there are, and this is pseudocode, but it allows us to talk about race conditions. And we let y be a new vector of the number of rows, and then we're going to go through and initialize y sub I to 0 for each of those, and then we're going to have a nested parallel loop, 1 to I, and then I to n, j to n, in a nested loop. And we're going to go through and pull the values out of the matrix, multiply it by this other vector, and then add it up. But we see that this causes a problem because multiple threads are writing to y sub I, and we don't know which thread is going to execute first. They're not happening in synchronized order. They're asynchronous. Once we say parallel, we don't have a guarantee of what's going to happen in order. It would slow it down tremendously if we had to just do them in a certain order. And so here we have the problem that multiple threads are using y sub I. They're reading from it and assigning to it. And so that's a problem. Let's look at this parallel square matrix multiply. We have 2 matrices. We're getting a number of rows, so we create a third matrix C that's an n by n. And in parallel, we go through, we initialize it, and then we have a loop for n values, to go through all the values of k, to go through and add them up. So what about here? Where's the race condition here? Think about that for a second. Well, there actually isn't one, because only one thread is writing to Cij, and so because of that, then we're safe, and we're not having multiple threads working on it. And so here we have multiple threads working on it's because of the J loop that we're having multiple threads working on the Y sub I, and that's what creates our race condition. When we're combining results from different threads, we want to use reduction to make this work. And there's other ways, there's other things like reduction in OpenMP, but for an introduction, we want to reduce it, and we'll provide the variable name that we're going to use here. So here, the changes, we made X private, and we used the compiler directive reduction, and we're adding to it. We could subtract, but we're adding to sum, the variable here. So it knows that it needs to coordinate those, and that sum is going to have the result of everything. And so it's going to keep track of that, so that outside the loop we can use sum and it's going to be correct. And so if we do this second version here, and we recompile it, execute it, we get 3.14159. That's a lot better, and maybe even better is it doesn't change all the time. If we don't do the private variable or the private directive here, then different threads are going to be writing over X at different times, and so X is going to be a little bit off. It won't make a huge difference, but it will make a difference even in this simple example. And so we need to make X private, so each of the threads have their own X, because notice we're writing to it and then we're reading from it. And then we definitely need to add in the reduction there. Let's look at the results here. So how long does it take? My timing calculations were just over 1.5 seconds with one processor, 2 significantly less, but we can see it bottoms out here in about 1/4 second. Doesn't help to do any more. The user time is fairly flat. So let's look at the speed up. Speed up does really well to 8 threads. After that, it actually decreases, but and so we do pretty well, and so that's going to mean we're fairly efficient up till 8, but then after 8 the efficiency drops off. So let's talk about this more generically, that we often in code have parts that we can parallelize and then parts we don't need to, but they need to be calculated in order. And so we often have a lot of computation and then combining results. So if we had code that was a loop and we do a lot of computation and then we need to combine those results together, we could break this up and store it in an array, calculate the different parts, and then combine them. Now, why would we want to break that up? It'd make the overhead for the for loop extra, but what that does is allows us to parallelize the big computationally intense portion of it, break that down, but then on one thread to combine everything. And so that could greatly speed up the execution. There are different ways we can control loops with OpenMP. We can tell it how to schedule. We could tell it static with an optional chunk variable to statically assign them in a round-robin fashion. We could dynamically schedule them with an optional chunk and just grab work as it's completed. It could be guided, or it could be determined at runtime using the OMP schedule environment variable. So I thought it'd be interesting to show you going through a nested for loop here to schedule it. For example, dynamic and then a chunk size. We put that in a variable. If we set running the code where this is the user time, the system time, and we can see how it and the CPU usage here. If we specify that it's static, dynamic, guided, or static with 20, we get different results from how much it's utilizing it. And it's going to be problem specific to what's going to work best. And it's also problem size specific as well. But I just want to let you know that there's several things you could do to control. That's it for this video. Check out my other video about examples for parallel programming. Thank you.